Good luck. I'm sorry, Dr. Tag. I don't know if just me, but I can't hear you in the Zoom.
There you go. Okay, so I think we're good. Thank you for alerting me to the mic is not picking up. Are we good now?
Yes.
Okay. Very good. So but you guys saw the screenshot there, so we still know what problem we're trying to solve here. So how do we solve this? We can basically flatten the dice. Okay, so the way I'm going to look at this is we're flattening a dice. So it has one face up that has the 1 on it, and then the other side of the coin we have the 2, 3, 4, 5, 6. So instead of looking at a dice as a 6-face dice with 6 possibilities, we just have a coin that has 1 on one side and then 2, 3, 4, 5, 6 on the other side. Now, obviously, this coin is going to be very loaded, right? Because the chances of landing on the 1 is 1/6, and then the chances of landing on the other side would be 5/6. But what it does allow us to do is to turn this into the binomial distribution thing that we already know. So the answer to this question, okay, so the answer to this question is the probability is exactly this, okay? It's going to be 5 choose 3, because out of 5 coin tosses, we want 3 to be 1s. And then we have 1/6, okay? Because that's the chances of the probability of landing on the 1, and then this has to be raised to the power of 3, because we want 3 1s. So for the other 2 rows of the dice or the coin, we end up with the other probability, which is 5/6. But that would be raised to the power of 2 only, because those are the 2 remaining rows of the dice that we want something other than a 1, and the chances of each one of those rows is just going to be 5/6. Is that okay? So the probability turns out to be 0.03 something, which sounds about right. So that was a very good question to ask, because it is an extension of what we have talked about in this class. And as it turns out, there is a way to solve the problem just by recasting the problem into a format that we already understand. Are we doing okay so far, with this particular example? Okay, all right. So if that is okay, what we'll do instead is continuing on to the topic of the time complexity of algorithms. Okay, so that's what we'll do next. It's just a continuation. So I just added a new link into this particular module in Canvas. So let me point out what I just added. I added a link to a Wikipedia page called the Master Theorem. But before we go there, okay, we want to kind of go back to recursive definitions and algorithms. So that we can just kind of take a look at some additional recursive algorithms. So the Tower of Hanoi is a recursive algorithm. So this is the finished form of the Tower of Hanoi. So you can see how we are calling Hanoi recursively, but with n-1 disks to move. But we have to do it twice. And then in between, we have another Hanoi recursive call, but this time there's only 1 single disk. So it's not really that significant as a recursive call, because we know it is the end of the recursion already at that point. So now the question is, why do we want to turn things into a recursive form? Can we turn string compare into something that is recursive? So if you are taking CISP440 this semester, and there are a few people in this class who are, then you know, yep, we just talked about it yesterday. Okay, string compare can also be done recursively. String copy can be done recursively. Okay, so why do we want to convert things into a recursive way of looking at things? The answer has to do with the new slide or the link that I put into Canvas. Now, this is not something, okay, so I'm promising that this is not something that I can really ask in the final exam for this class. It does not mean it is not important. It simply means that for this class at this particular level, it is difficult to come up with questions to ask, regarding time complexity. So we're going to take a quick look at the master theorem. And since it is not going to be in the final exam, I'm just going to touch on this a little bit, okay? But it is still important. So the thing about the master theorem is it is looking at a general format of looking at the time complexity function like this one here, okay? And you put a mouse pointer to which is this portion here. So in order to solve a problem of size n, or the amount of time to solve a problem of size n, we basically turn it into something like this. So A is a multiplier, B is a divider. So we are dividing the original problem into subproblems. Each one of the subproblems has a size of n divided by b. So B is kind of like how much are you chopping down the big problem into smaller problems. And then A basically saying, how many of those subproblems do we have to deal with? Sometimes B is much greater than A, other times they are the same. Okay? And then f of n is representing, not counting the recursive call, what is the overhead for just solving a problem of size n? Not counting the recursive call. Are we doing okay so far? So the relationship between A, B, and f of n will determine what class the time complexity is going to belong to. So let's go ahead and take a look at certain well-known algorithms that we already know, and then we'll try to see if we can figure that part out. So let's look at linear search, okay? I hope you guys still remember linear search, because that should be a topic that we talk about all the way back to CISP440. Is that okay? Are we good so far? All right. So let's look at linear search. And we are going to assume that the array is not sorted. So you cannot just say, oh, we'll search until the element is greater than the value that we're looking for, because at that point we can just kind of give up. So we do not assume anything about the array. It is not sorted. So if the element of what you're looking for is not in the array, you really kind of have to go all the way to the end to confirm that it's not in the array. Are we doing okay so far with that? So you look at this and go like, I do not know of a way to do linear search recursively. Sure you do. So how do you do linear search recursively? So I'll just pretend that I'm the first invocation, okay? I'm given an array, okay, and given a value to search, and I just need to answer, is this thing in the array or not, right? I look at this problem and go like, I'm just going to pick one thing out of the entire array to do the compare because I'm lazy, okay? So I pick either the first one or the last one or somewhere in the middle, okay, and say, no, that's not what I'm looking for. So what do I do next? I chop the array into two halves, okay? And then I give one half to you, and it's the same nature. It's like, can you find this thing into this smaller one half of the array? And I'll give the other half to you. So if one of you comes back and say, yep, I found it, then I just kind of report that back to whatever is calling me to find whether the value is in the array or not. Are we doing okay so far with that technique? Turning something that is inherently not really recursive into something that is recursive. Okay. So in that case, what would be A? What would be B? And what would be f of n? So let's think about that a little bit. Okay. First of all, let's focus on B. What do you think B is going to be? I break the array into two halves. So it'll be 2. B is going to be 2. What about A? How many times do I have to call recursively? Twice, okay? In the worst case, twice, because I would call you first and say, this is the first half of the array. Can you find this value in that first half of the array? If you come back and say, yes, you found it, I don't have to do the second call. But in the worst case, where the element is not in the array, then you come back and say, no, I cannot find it. Then I'm going to call recursively again and say, can you find the item in the second half of the array? So in the worst case, A is going to be 2 also. So A and B would be the same. Is that okay? What about f of n? In other words, not counting the time for the recursive call, just counting what I have to do. How does that have anything to do with the size of the array? It's a trick question, by the way. The answer is nothing, because I'm just picking one element and take a look at it. That's a constant time operation. So that means f of n in this case is just some kind of constant. Like we can call it just k. Okay. So now, what this table is showing us is if we know the relationship between A, B, and the general idea of what f of n looks like, we can find the general class of time complexity. So we'll look at the first one where it says f of n belongs to some big O, meaning that n to the power of something is the upper bound of f of n itself. Now remember what f of n is representing. F of n is representing the amount of work that I have to do in relation to the size of the problem. In this particular case, it is a constant. So now the question is, is the constant function an element of big omicron of n to the power of something? The answer is yes. Okay. Okay, so the first requirement is met. And then we also have to look at C crit. Okay, C crit is defined here as log B of A. Now we are in a situation where B and A are the same. So in other words, we are looking at log 2 of 2. What is log 2 of 2? 1. It's 1, exactly, because 2 to the power of 1 is 2. Okay, so now the question is, can I find a C that is less than 1 such that the constant function is an element of the big omicron of n to the power of that thing? Sure, because a constant function is basically big omicron of 1. That is the tightest bound for anything that has a constant time, right? And 1 itself is n to the power of 0. Is 0 less than 1? Yes. Okay, so we have met this requirement already. And then the other requirement, okay. So now we have the tight bound of its big omicron n to the power of secret. Can someone remind me again, what is secret? Secret is log 2 of 2 in this case, which is 1, right? So that means that the tight bound is n to the power of 1, which is otherwise known as what? Just n, right? N to the power of 1 is just n, which is the linear time complexity. So linear search has a linear time complexity. I don't think anyone is going to argue with that. Is that okay? All right. So let's take a look at another example, binary search. So binary search does require an array to be sorted to begin with, but that's just part of what the algorithm requires. We are more concerned about the time complexity than what the algorithm needs. Okay. So in that case, in binary search, what do you think are A, B, and f of n? First of all, can we look at binary search recursively? If I can strong arm linear search into a recursive format, I think binary search is much more natively recursive. Okay, so this time I'm given an array, right? It is sorted already. I'm given a value that I'm supposed to find within the array. So TAC is going to do the lazy thing. Look at the entire array that I'm given with, find the one in the middle, and just compare to that thing. So once again, we have a constant time overhead. F of n is just a constant time k of some sort. It does not even depend on n. Is that okay? What is different this time is because of the comparison of the value versus the middle element in the array, I really only have 1/2 of the array to continue to look into if that element is not matching. Does that make sense? Okay, so that means, of the two potential recursive call, I only need one of them, not both. So that means we are changing the ratio between A and B because B continues to be 2, but A is 1 this time. Is that okay?
Why is A1?
Hmm?
Why is A1?
A is 1 because in binary search, you only have to go for the recursive call for the first half of the array or the second half of the array, never both at the same time. Because by determining how the value that you're supposed to find, how it relates to the middle element, you can eliminate 1/2 of the array and say this half of the array cannot possibly have the value that I'm searching for. So that means your recursive call only has to deal with the other half that can still potentially contain the value that you're looking for. So that's why A is 1, but B is still 2. Okay. F of n in this case is still constant time because I only have one single element to compare to, which is a constant time operation. So now what do we know about this thing here? So we look at the requirement. So the first thing we need to do is look at secret. So in this case, secret is going to be log 2 of 1. So can someone tell me what is log 2 of 1? 0. That is correct. So secret is going to be 0 in this case. And then we now ask, is constant time, going to meet this requirement? The answer is no, okay? Because if secret is 0 already, we're looking for now a negative value of the big O notation, and that's not going to work. Okay, we are not looking at a fraction of, based on n. We are at the best algorithm is just going to have C being 0 itself. So the first category is not going to work in this case. So now we look into the second, category here. And then the first thing we need to know is, can we apply that? So when f of n is big theta of n to the power of secret, which is 0 in this case. So we have 1 times log k of n for some k that is greater than or equal to 0. This k, by the way, normally the way I write it is down here, but some people write it up there too. So we're looking at log k of n for some k that is greater than or equal to 0. Well, is that going to work for us? So what k, are we going to choose in this case? K is a constant, k is not n. So the answer is no, I don't think it meets, we can find anything to meet that requirement here. So now we move on, and there are some subcases here. I'm just trying to shortcut to find the answer that we are looking for. So we are, in the end, we're looking for big theta of log of n. Big theta, they all involve, the 1/2 power of 1/2 here. But that's just an example. And grid log k plus 1 of n. That will work. So this one should work. Okay, so let's see how we can make these numbers work. Secret, we are done with that already. Okay, secret itself has to be 0. So n to the power of 0 is just 1. Okay, that's all good. So now the question is, can we find a k that is greater than or equal to 0 so that f of n is have a type bound of log k of n? So what do you think? It has to be a type bound. That's the only problem. Because we want a constant time. F of n has a type bound of a constant time. So the question is, can we cast a constant time complexity to be a log k, k can be whatever we need it to be of n. So we want log k of n to be 1. And that is going to be difficult because I don't think we can find a constant k that can do that. So whatever we find is going to be an upper bound. It's not going to be a tight bound. I take it back. Okay, I take this back because I was confusing myself of what is log k of n. In this case, the k is log n to the power of k. I think that's what it's representing. So in that case, it's easy because k just has to be 0. Then we have our solution. So since we can find a k to make this work, then the solution, which is the time complexity of the size of problem n, is sec theta, which is the tight bound, of n to the power of 0, which means that this component goes away. And then k is 0. So we have just log n to the power of 1, which is exactly what we have for binary search. So it does work in this case. So do you see the magical thing that we are doing here? By analyzing the recursive implementation of an algorithm, just by figuring out what is A, what is B, what is secret, and try to figure out K in this case, we can sequentially go through these scenarios and be able to figure out what is the time complexity without actually needing to go through all the analysis process associated with the algorithm itself. Is that okay so far? So this is called the master theorem. And the master theorem, because of the way we want to cast the time complexity, depends on recursive definitions. And that's why I talked about recursive definitions earlier on Monday, because that is a prerequisite to be able to utilize the master theorem. Are we doing okay so far with all this? Maybe. For those of you who are not in my CISP440 class, do you guys want to see an example of string compare turned into a recursive definition? Or are you guys okay? Sure, we can do that. All right. And some of you have taken CISP440 from me before, so you should remember those examples too. I'm laughing in an evil way because I know most of you do not remember. All right, so we're going to look at string compare. Okay, so cons char star PA, cons char star PB. So a normal person would look at your string compare and do it with a loop. There are many ways to do it in the loop. One way to do it in the loop, okay, so I can do a int result, okay, and then the way we do this is, okay, and then over here we turn result. All right, so I'm going to write this loop here. Result equals to star PA minus star PB. Okay, put these in parentheses. And then we say if this is not 0, if it's not 0, no, if it's not 0, we get out of the loop. So we want to say if it is 0, okay. And this editor does not have parentheses matching, so that's why I have to do all the matching myself. Okay, so this open close here that equal to 0. And we also need one more thing to continue with the loop. So we need to make sure that PA is not null. So we have to make sure that that is not null. And I put one additional pair of parentheses all the way top of this. And then in the loop, all we have to do is to increment the pointer PA and increment the pointer of PB. That's all we need to do. That's the loop way of doing things. And it is not a typo. This really is an assignment operation. Assignment is an operator in C++ or C. It is not a statement. So that means you can embed an assignment inside any expression that you want. It is both a feature and a curse. because you can sometimes accidentally, you meant to use equal, and then you forget to type that extra equal. The C compiler goes like, well, I trust that you know what you're doing, so I'll just let you do it. Now, a modern day compiler, okay, including GCC, you can turn it into, you can warn all, it's a W dash uppercase W lowercase ALL. So it's going to give you every single possible warning, including in this case, if I did not put in the extra parentheses here, it would have given me a warning and say, okay, this looks suspicious. Do you really mean assignment and not comparison? Okay. But if you don't turn on those additional warning features in C++, syntactically, this is perfectly okay. The compiler would just go like, yeah, I trust that you know what you're doing. It's fine. Questions? No? Okay. So this would be the normal way of doing string compare. And I do use a lot of shortcuts by using an assignment inside the comparison condition and combining everything into one single condition. So, but it is nonetheless non-recursive. Okay. So the question is, how do we turn this into something that's recursive? So this is how. In string compare, const char PA, const char PB, char PB, and you simply return, and this is something that I talked about in the class in CISP440 yesterday, so some of you may be bored at this point. So if PA and PB are different, does not equal to PB, then I don't need a recursion anymore, because at this point I have found that the two strings are different. And if you look up the definition of string compare, it returns a negative value when string A is less than string B. It returns a positive integer if string A is greater than string B. So that means my return value only has to be this. But what if that is not the case? Well, this is the else. So in the else, we ask, so PA, whatever PA points to and whatever PB points to are exactly the same. I cannot determine the ordering yet. Okay. So now the question that I need to ask is, are they both pointing to a null character? Because if they are pointing to a non-null character, then we have to call string compare recursively. So this is where string compare is called recursively, with PA replaced by PA plus 1, PB replaced by PB plus 1, because this way I am basically just moving on to the next element of each array, okay, which is considered as a quote-unquote substring, right? And say, okay, tell me how the substrings compare, because the character that I'm looking at in the string, they are the same. Okay, so look at the substring and tell me how they compare, and that becomes my own answer to whoever called me in the first place. And the else corresponding to this condition is simply a 0, because in that case we are basically saying PA and PB are the same, so that we can get here. And then PA is pointing to a null character, which means PB is also pointing to a null character, which means I cannot determine the order at all. You are giving me two empty strings, and the two empty strings will be considered the same, and therefore I return a 0. So this is the recursive way of doing string compare. So we still do okay so far with this? Okay. But it is the ability to turn something from iterative into recursive that allowed us to apply the master theorem. And therefore, we can basically figure out the time complexity just by looking at how we break up the larger problem, how many pieces do we break it up into, and how many of those pieces do I need to call recursively, and also how much work I have to do not counting the recursive call. Knowing those three pieces allows me to understand what class of time complexity it belongs to. So this is a really useful technique of figuring out the time complexity of an algorithm if you can basically cast the algorithm in a way to fit in this particular time complexity format. All right. Are we doing okay so far? Okay. How about merge sort? Do you guys still remember merge sort? And then if you do remember, the question is which version of merge sort do you remember? Because there are two main variants of merge sort. One is intended to be done in place using an array, and the other one is intended to be done using tapes. Okay, with those mainframe computers. Tapes. Oh. I can see a generation gap here. Okay, so I'm gonna look up an IBM mainframe tape drive. There we go. Oh, these are too modern. Let's look up ancient. There we go. Oh, it's a video. Okay, so I'm just gonna pause here. These things back here, those are the tape drives. So back in the good old days, this is how mass store is about. I mean, one of these tape probably has the same capacity as, I'm gonna guess, maybe a few megabytes. So you can have a whole stack of these tapes and it will still contain less storage than an SD card that you now these days to be used, like a TF card, which literally can be eaten by a dog. You can now say, my homework is, my dog ate my homework, because you put your homework, your file onto a TF card. And I can easily see a dog, even the Chihuahua, of chewing up and eating your TF card. Then you can tell your professor, my dog ate my homework. It's easier for your dog to eat your homework now these days than decades ago. So anyhow, so the problem with tape is they are not random access devices. TF cards are great for random access. Okay, I need to get right in the middle of this file. Easy peasy, not a problem. Even hard drives, even though it's not truly a random access device, it's still relatively fast. Now, I say it's not a truly random access device because depending on which track or which cylinder we are talking about, the disk head actually has to physically move across the surface of the platter. And then you have to wait for the rotation so that the right sector will be right under the disk head. So it's not really truly random access, but we'll call it random access enough so it doesn't make a big difference. Okay. So these things are very slow with random access. You don't want to do random access with these things. Merge sort is great with these tapes, because what you do is you have the original tape containing the unsorted records, okay? And it's split into two output or two tapes as the output. So each tape only has to go in one direction at a time. Okay? All three tapes are going forward. So by splitting the original tape, you're writing into the two tapes as the split outcome of that operation. And then when you're merging, then you're turning the whole thing around. The two tapes containing the split result turn around and become the input, and then the one tape becomes the output. So just by changing the role of the two tapes, of the three tapes, sorry, you just have to kind of go this way, again and again, log n times, and then the original thing is sorted. So it's a very smart algorithm. Okay, I have to say it is really one of those kind of really ingenious algorithms because it works so well with older hardware. I'm going to digress a little bit here because I'm going to say it is still applicable today. So you might say, but Tech, we got lots of RAM. We got 32 gig on my laptop computer. I can fit the entire array into RAM. So why would this still matter compared to the other implementation of merge? So it has to do with DDR technology. So how many of you know what is DDR? Okay, go ahead. It's double data rate, okay, but what is it? I mean, what is the relevance of DDR in today's technologies term? Why do we want DDR? What does it do? I mean, why is it faster? Because if it's not faster, we wouldn't be using it. So what does it do? What is that double data rate? It's actually quadrupling sometimes, okay? But the thing is, why is it faster, right? Now, if you think about the term, double data rate, obviously doubling is better, right? But it comes with a certain sacrifice, okay? Because in order to set up the double data rate mode of operation, there's a little overhead to it. So instead of grabbing only one location at a time, DDR technology will take a block of memory at a time. In other words, your program transparent to you, you say, I want to go there and grab those 64 bits, okay, 8 bytes. And then using DDR technology, the memory controller combined with the cache is going to say, great, okay, so we'll go to that block over there, and I'm going to grab, I'm just making this up, 128 bytes, okay? So the original 8 bytes that you request will be the first of the 128 bytes. It's going to read all 128 bytes, but really fast using the double data rate technology into the cache on your processor. Okay, so now you're going to say, but I only asked for 8, okay, but you're giving me 128. So that means you have a read ahead buffer or FIFO kind of thing. So with merge sort, if your array can only go forward, both the one that is incoming and the 2 that are outgoing, if you're only doing it in a linear fashion, the reading ahead is great, right? Because you're going to need it anyway. A random access algorithm like quicksort, which is truly random, it's all over the place, okay? That means you'll be wasting a lot of memory cycles because a lot of the stuff that you're reading may not be needed, and it needs to be paged out from the cache of your processor anyway. So even with today's technology, even with the DDR technology, I still think merge sort is relevant. Okay, how you're accessing an array instead of going all over the place, kind of in a random order. If you go in one single direction linearly, it is still going to be faster compared to the random access. Now, how much faster? That's I don't know the exact number, but I think just because of the way the hardware is arranged, it is going to be faster. Yep.
This might be more of a 310 thing, but from what I understood was that they can transfer data from like the rising and falling edge of the CPU. So what does that mean? How does it work on the falling edge?
Sometimes it's not. It's even faster than that because it's a timing thing. So normally in using fully synchronous access, the processor will basically say, this is the address, I want to read operation and start the operation. So typically you need to even insert additional wait states because RAM is slow, okay? So right after it understands which location you want to access, it takes time for the chip itself to get to that location so that it can present the content at the database. So you need additional wait states to actually just artificial wait for the RAM to respond to you. So, but once it responds to you, double data rate basically says, okay, once this is all set up, give me the next bunch of locations. So in that case, it becomes an asynchronous operation, or because it's based on timing. So the processor is basically saying, I'm expecting one memory refresh on the bus every this many nanoseconds, and then the RAM has to be consistent with that. So not only are you giving one single result for the rising edge and one result for the falling edge, you can have one transfer between the edges. As long as the processor can, as long as the timing is consistent enough between the processor and the RAM, you can fit one more transfer even between the edges. So that's why we have DDR, DDR2, DDR3, DDR4, DDR5, because they just use a different protocol between the processor and the RAM in order to say, okay, now that we have spent the overhead to get to this location, getting to the next location is this easy. Why not? So the only question is, how many of the following locations do you want me to give you? And can they be programmable? Can I say the 16 locations, 32 locations after that? So I think those are some of the differences between the various standards of DDR. DDR5 is not always faster than DDR4. It depends on the access pattern. All right, so getting back to this entire discussion, time complexity is important. Okay, we really need to pay attention to how an algorithm scales up as the size of the problem scales up. Is that okay so far? All right. And there's really not much that I want to continue to talk about in terms of time complexity. There's one class of problems that you also might want to pay attention to. I'm not really sure whether that is going to be a topic in a 4U university anymore. Yep.
Actually, like in an undergraduate for the setting, to what extent are we expected to know about time complexity algorithm analysis?
That's a very good question. So let me see if I can find the answer to that. So we will look up typically this is the title of the class that will talk about this sort of thing. It is called the analysis of algorithms, and we'll look up a particular campus. So UC Davis. See if what is going to come up here. All right.
Yeah, I'm confused because are they graduate classes or are they?
They're undergraduate classes. There are equivalent graduate classes too, but I think some of these, the 122A would be an undergraduate. The 222 is a graduate level class. So we will look up the undergrad version of this class. All right, so we'll look at the description. Complexity, typically they look at both space complexity, how much space does it take to solve the problem, and also more importantly, most of the time, the time complexity. Bounds on complexity, upper bound, upper bound and lower bound, right? That would be Omicron and Omega that we talked about. Type bound, which is our big data. Analysis methods, okay, which we just kind of touched on today a little bit. Okay, the master theorem is really just one of the techniques in order to analyze the time complexity of algorithms. They would generally talk about searching, sorting, pattern matching, and other types of graph theory algorithms. We'll talk about Dijkstra's algorithm and also the A-star algorithm in this class. Algorithm design techniques, divide and conquer, greedy algorithm, dynamic programming. We don't talk about the dynamic programming in this class, but I think in Raj's class we might have talked about dynamic programming a little bit. But divide and conquer is typically the indicator of a recursive algorithm. Binary search is definitely divide and conquer. Okay. Greedy algorithm, we'll get to that. Okay, by the time we get to the A-star algorithm and also Dijkstra's algorithms, those are greedy algorithms. Approximation methods, NP complete problems. So I'm going to give you a little bit of what NP complete means. I'll only talk about the why you need to know it, but not so much, all the details about it, because there's simply not enough time to talk about what is the technical detail of the NP. Okay, so I'll give you this example. So let's just say that you are working for a pizza delivery service. Okay, you're working for a pizza shop, and your job is to deliver pizzas. So can someone tell me what would be a realistic number of stops for a pizza delivery car? 4 or 5, because any more than that, the pizza is going to get cold, and then your client is not going to be happy to get cold pizza. Okay, so 4 hops. Okay. So now you have 4 customers in a certain neighborhood, and you need to write an algorithm to find out, okay, what is the best way to route, what is the best route to drop off those 4 pizzas at these 4 addresses? So would that be a difficult thing to do? It's an easy thing to do, okay? Because you can just basically figure out 4 factorial alternatives, right? So let's call the 4 destinations or the 4 addresses A, B, C, and D. Okay, how many ways can I arrange, how to traverse between those 4 addresses? 4 factorial. Okay, because you can choose A, B, C, or D as the first destination. But once you have chosen A as your first destination, then your second destination can only be B, C, or D, and so on. Okay, so it's 4 factorial. Is 4 factorial a large number? What is it exactly? It's 4 times 3 times 2 times 1. It is 24. I'm pretty sure modern day computers, including your smartwatch, can handle 24 alternatives. It just has to use the API to Google Maps, find out exactly how much time to it would take between the points, and then find out of the 24 possible ways which one is the best. And then it would just give you the route and go like, okay, this is your first stop, this is your second stop, this is your third stop, and this is your 4th stop. Done, right? So your boss, who owns the pizza place, decides this is such a great little program, okay? And your boss decides, I got a friend who runs a courier, service like UPS or FedEx, and that guy seems to be always having problem with the drivers not knowing what is the best route to drop off the packages. So your boss decides I'm going to share this program with my friend who runs a courier service. And then the next week you go to work, you're fired. Your boss doesn't like you anymore. Why? You ask your boss. It's like, last week you were just so happy that I was able to get all the pizzas delivered in an optimal time frame. So why are you firing this week? Your boss says, you embarrass me. You go like, what? I gave this program to my friend and it's still running. I mean, it ran over the entire weekend. It's still running. Your program doesn't work. So why do you think that is the case?
It didn't scale well.
It did not scale up. Yeah. So what is the typical estimate of the number of stops that a typical UPS truck needs to stop on a particular day? Let's just call it 100. Okay, let's just say 100. Okay, so how does 100 factorial compares to 4 factorial? You go like 25 times, right? Not really. I can tell you one thing, okay? I don't know exactly what is 100 factorial, but it's a huge number. Why do I not? What? Okay, so let me describe it. I know you know the answer. I had a Casio calculator, when I was in middle school or high school, and the calculator has an upper range of scientific notation, like what is the largest value it can represent, which is 9.99999 times 10 to the power of 99. Okay, that's a pretty good size number, right? 16.9 factorial is the last factorial that you can calculate. 70 factorial is already beyond the range of my calculator. And we are looking at what? 100 factorial. So that's why the program seems to be hanging, because it is taking so much time. There are so many ways to arrange all the possible destinations, how to order the destinations when you have 100. That problem is also known as the traveling salesman problem. Okay, some of you might have heard of the traveling salesman problem. It is the classic problem representing the NP complete class of problems. So that means NP complete is not describing a particular problem. It is describing an entire class of problems. So as long as whatever problem you need to solve can be converted into the traveling salesman problem using polynomial time, your problem belongs to the NP complete class. So what is the big deal of that, right? So let's get back to reality. It's like, what are we going to do with this? Because now you can present to your boss and say, well, it's an NP complete problem. Your boss says, well, I just have to fire you and get someone who's smarter. You can now say, nobody has solved this problem. The likelihood of you being able to hire someone to solve this problem is practically zero. So even if you fire me, you're not going to solve the problem. So that is how you can use your knowledge of NP completeness and algorithm analysis to save your job. And then you go like, well, thanks to tech, teaching this class, I get to keep my job, as the driver, for a Pizza Hut or Pizza Place.
Is that our future after ChatGPT?
I think with ChatGPT and the drones and whatnot, there won't be anyone driving around the people.
True. It'll just, eventually we'll just teleport them or 3D print.
That might actually be 3D printing has a different, it has something that's going to be interesting because you don't need to buy stuff anymore. You just 3D print it. I need a plate. Yeah, that's the Star Trek fabricator thing, right? You can fabricate whatever you need. All right, so I think hopefully this gives you guys an idea of what you can expect when you move on to a 4-year university. I think Davis is average, amongst all the UCs, not particularly hard, not particularly easy. So this is what you can expect. We good? All right. So what we'll do now, okay, since I did promise you that I will not ask you any questions related to time complexity, so we're going to move on to something that I will ask you questions about, which have to do with the graph algorithms. So now we're moving on to graphs, and this would be a good time to jot down in your notes of today's date and the current time, so that when we start to talk about graphs. So if you need to go revisit the lecture, you know where to go back to in terms of the recorded lectures. All right, so this starts off with, a graph is represented by a tuple. B is a set of vertices. E is a set of edges. Okay, so now you're going like, okay, so what is a vertex and what is an edge? A vertex can be anything. Okay, so the set of vertices can be a set of whatever you want. Okay, there's no limitation. Okay, there are no limitations as to what you can use as a set of vertices. So typically I just use A, B, C, D, F or something like that, to represent vertices. Now edges, on the other hand, has a limitation. The set of edges has to be a subset of the Cartesian product of the vertices, and itself. Is that okay so far? Are we still remembering what is the Cartesian product of two sets? Okay. And we look at this and go like, I remember we see this as a relation thing. Yes, but this is a slightly different context. So this means that each edge is a two-tuple where the first item, called the tail of an edge, and the second item, called the head of an edge, are both elements of the set of vertices. Are we still doing okay so far with this description? I will show you an example later on so that you guys can say, oh, so if a graph looks like this, then it's represented in set like this. Okay, so we'll go through an example today, and I think we still have plenty of time today to do that. Okay, so now the question is, why is the first item called the tail, and then the second item in the two-tuple called a head? It has to do with how we draw an arrow. The arrow is implicitly saying that we're going from the first item in the two-tuple to the second item. And the first item becomes the tail of an arrow, and then the second item becomes the head of an arrow, because that's how we draw arrows. That's how we indicate direction. So now would be a good time for me to show you an example of a graph and how it is represented by a set or two sets in this case. So let me get that set up. Give me a second here. All right. All right. So this is what you guys will see. And then on my side, I have to do a few things to get this to work. All right, so I'm gonna make a new page. So now I can actually draw a graph. So we'll draw a graph like so. We have node A, we have node B, C, node D, A goes to B, B goes to C, C can go back to A, and then B can go to D, and so can C. Okay. So as a hand drawn graph, do we understand what this is representing? Node A can go to node B directly. Okay, it doesn't edge between them. Node A cannot go to node B directly. You have to go through D to get to D. Node C can go to A or D, but node C cannot go back to node B directly. Is that okay? So this is basically what we call a digraph or a directed graph, because the edges are directed, they're directional. Is that okay? So now, how do we represent this using the set notation? So V in this case is going to consist of A, B, C, D, because those are the names of the vertices. What is more interesting is what is in E for the edges, the set of edges. So now we have AB as a two tuple. We have BC as a two tuple. We have CA as a two tuple. We have CD as a two tuple. And then finally, we have BD also as a two tuple. So is that okay? The set of vertices is just A, B, C, and D. The set of edges consists of two tuples, where each two tuple is representing an arrow in the graphical representation. The tail of an arrow is the first item of the two tuple. The head of the arrow becomes the second item of the two tuple. Do we have any questions about the representation of a graph? In this case, we're dealing with a digraph or a directed graph, which means there are graphs that are not directed, which means the connections are bidirectional. So we doing okay so far? All right. So what does this have anything to do with computer science? I mean, why would we care about graphs in computer science? What do you think graphs can represent? Well, let's think about things that we do and we use on a daily basis. What do you think a graph can represent that you might use, every few days or so?
Map.
A map, very good. Okay, so a map can be represented by a graph. And in the case of a map, every single node is corresponding to an intersection. And then the edges are corresponding to where that intersection leads to directly. And then basically each edge is representing a segment of the road between two intersections. Does that make sense? Okay. Then the next question is, do we want to use a digraph, a directed graph to represent a map, or do we want to use a undirectional or non-directional graph to represent a map? In other words, can we assume if it takes me this much time from point A to point B, it will take me exactly the same amount of time from point B to point A in the context of a graph, of a map.
Unless the road is one way. Unless the road is comparative.
Some roads, some streets are one way, exactly. In Sacramento, we have some of those, downtown, but not a whole lot. But in San Francisco, there are a lot of one-way streets, right? So in the case of a one-way street, you really want to use a digraph or a directed graph instead of a general graph that has no direction. So typically, a digraph is more general because if you want to represent, you can go between A and C, it's bidirectional. That's easy. All you have to do is to add another edge like so, And now you can go from A to C and also from C to A. Is that okay? So you can always represent bidirection attributes, even with a directed graph. All right. Any questions at this point? What do you do with a map? That's a very general question,
Figure out.
That is one use of a map. And if you're like me in the good old days when we go to AAA to get the actual map, you can also use it to kind of use it as a sunshade, right? Or in the winter, you can use it to start a fire. Okay, there are a lot of uses of a paper map back in those days. Okay, so yes, we want to use a map to navigate. Okay. And when you're navigating between a point where you are to the destination of where you want to go, what do you think is one of the objectives?
The optimal way to get there.
Trying to find the optimal path, which usually translates to either the fastest path or the path that will save you the most fuel, or the path that will give you, make it possible if you're driving a Tesla, because you might need to charge your vehicle in between. So you need, you have extra constraints in those cases that you need to make sure that before your battery runs dry, that you have a place to be charging. Okay, very good. So we do, but generally speaking, we just want to be there as quickly as possible. Okay, so that basically describes the two algorithms that we are going to deal with. One is called Dijkstra's algorithm. Can anyone guess why it is called Dijkstra's algorithm? It is the name, it's the person who invented the algorithm. Very good. Okay, so let's take a quick look. I promise this is just going to be a quick look at the author, Dijkstra, 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 and we want to look it up in Wikipedia. So Wikipedia. I don't know about you, but I find that it is helpful to kind of understand the historical thing about these people. So Esger, I'm not even sure whether the S is silent or not. But basically, Dijkstra is one of the two modern fathers of computer science. So the father of computer science is Alan Turing, at the end of World War II, or close to the end of World War II. But Dijkstra and Knuth are the two modern father of computer science. Together, they wrote most of the useful algorithms that you will see when you get to a four-year university. Okay, so I think Knuth wrote a 3-volume set of books on algorithms. And then Dijkstra also contributed a lot to the algorithms that we typically use. So Dijkstra's algorithm at one point is considered AI because it was able to solve problems that people were able to solve, but prior to Dijkstra's algorithm, there were no algorithms to solve those problems. So AI, or what we consider to be artificial intelligence, is really right at the edge of what computers can do and what we want the computer to be able to do. That edge, okay, is what AI really is. So if you ask anyone today and say, is Dijkstra's algorithm considered AI? The answer is no. Okay, it's a very simple algorithm that we can describe in this class in about, I think, 40 minutes or so. Okay, I cannot finish describing it in today, in the next 10 minutes, but nonetheless, it is not artificial intelligence. Okay, it's not considered artificial intelligence anymore. But back in those days, it was. All right, so this is Dijkstra's algorithm, and I'm not sure about Iraj because we typically cover Dijkstra's algorithm at about the same time. No, not yet. Okay, all right.
Final week.
Getting close.
It was the final week we covered last semester.
Oh, okay. So what we'll do is we'll take a really quick look at the algorithm itself and just get familiarized with the concept here. It doesn't use any notation that we have not talked about so far. So this is what I say, this is what I mean when I said the final exam is not intentionally comprehensive. Because I'll be referring to notations that we have been using this entire semester, but I'm not going to test you on just those notations. They will just be a utility, in the newer problems. All right, so we'll read the sentences one by one. Let the graph be G is VE, V is the set of vertices, E is the set of edges. And then we have this notation here. It is described here. This is a function notation. So the function notation says that V is a function. It maps edges to non-negative real numbers. In other words, we have a quote unquote distance function. That's why it's called V. It is a distance function. If you specify an edge, the distance function will say, this in order to traverse this edge, it's going to cost you this much. But this much what? We don't care. Okay, it's just a value. Can be time, can be fuel, can be a combination, like a weighted, number of sorts. Okay, we don't care what it is, but it is basically a distance of an edge. Now, this is where the algorithm that Iraq will describe is different from the one that I described. So this time, we have S being a subset of V, being all the destinations. In other words, the Dijkstra's algorithm that I use in this class can deal with multiple destinations. You guys go like, that doesn't make sense. Why do we want multiple destinations? I want to go to, sushi cafe. Why do I want to know, how to get to that restaurant over there, that restaurant over there? Yep.
Because maybe you want to visit something in the middle of your trip and then get to your destination. And
not quite, okay, not quite. Imagine that you are a chaperone to, with some first graders to the Discovery Park, Six Flags, okay? Not something that I really want to do again, but just imagine. So you're the adult, you're responsible for like, six, first graders. And then, right after a show, they come out, and go like, I need to go to the bathroom. Of course they do, right? So now I think you're starting to understand why multiple destinations make sense. Because there are multiple bathrooms in Six Flags, or we will definitely hope there are multiple bathrooms in Six Flags. So the question is, do we really need to go to a particular bathroom, or any bathroom will do, right? So that is why an algorithm that can deal with multiple destinations actually makes sense in certain scenarios. So in this case, S would be a set of all the possible bathrooms. V would be all the intersections, all the different places they can be that is on the map in Six Flags. So the algorithm would initialize certain things. So for every vertex V as a destination in the set S, L of V is initialized to be 0. So this notation here is an assignment. L of V is initialized to 0. So L is a function, and I'll describe that function later on of what it really means. And then for every V that is not a destination, L of V is initialized to infinity. Is that okay? Line 3 and line 4 are for the initialization of the function L. The L of a destination is 0. The L of a non-destination is infinity. So basically what L, yeah, go ahead.
So like destination as in like in Six Flags, you got bathrooms, you got restaurants, you got attractions. So all the S's that are restrooms are 0 and the rest are just infinity.
That is correct. Yep. Because what L is representing is the length of the shortest path to that particular vertex. Okay. Does it make sense? Okay. Does it make sense that the destination has an L value of 0? So let me ask you this question. You're standing at the destination, you're standing right next to a bathroom. And what is the distance to get to the closest bathroom? 0 distance, because you're there already, right? So that is why the L value or the L function is initialized to be 0 for the destination vertices. What about the non-destination vertices? Why are they initialized to infinity? Because we don't even know whether they are connected or not. So we make the worst case, assumption that they may not even be connected. So that's why those are all initialized to infinity. And then the next thing we do is we create a new set called Q. We initialize Q to be the same as S. And then we initialize E prime to be an empty set. This is going to be the set of the quote-unquote solution edges. And then the following is the algorithm. It's a while loop. Inside the while loop, we have two things that we need to do. Inside that, after that, we have a for each loop. Inside the for each loop, we have a conditional statement. And that's pretty much the entire algorithm. It's not a very complex algorithm. So we're still doing okay so far with the symbols. Okay. Assuming that is okay, so I think we got something to read over the weekend because next Monday, I am going to apply this algorithm to an example graph. Okay, so in other words, we'll be tracing the execution of this algorithm on an actual graph. So you probably want to make sure that you understand the notation, so that way you can follow all the steps that we are going to do in the lecture next Monday. So the algorithm says, as long as Q is not empty, do the following. So that means the only way we can end the loop is when Q becomes empty. The first thing we do is this entire sentence here. And if we want to select a vertex V that is an element of Q such that blah, blah, blah. So I think, we'll go ahead and finish this entire sentence, and that would be a good end of today's lecture. But I would still want you guys to read the entire thing and make sure that you understand at least the symbol. Okay, so we'll focus on this quantified statement here. What is it really saying? It says, for all W in Q, L of V is less than or equal to L of W. What is an easier way to say this? So let me start from the beginning. We want to select V, which is an element of Q, such that for all W in Q, L of V is less than or equal to L of W. I mean, the answer is right next to it, because I have the English explanation right after the expression. Okay, so let me read it by myself. V has the shortest length to a destination of all the other vertices in Q. Does that make sense to you? Yes.
So for all other vertices, all other paths, V is the shortest.
Of all the vertices in Q, V has the shortest known path to a destination.
Because it's zero.
No. We don't know what it is, okay? Because remember, the initial state is that Q is the same as S. But as this algorithm progresses, we don't really know. So the only thing we know from this sentence here is of all the vertices in Q, we choose the one that has the smallest L value, which translates to of all the vertices in Q, the vertex that we choose to use in this case as V is closest to a destination.
How do you know that? That's what you're trying to find out.
No, as we work through this algorithm, the L values will be calculated. So we have some partial results, as we go through this algorithm. Yep.
The second bullet point, the Q implies Q minus the set of V.
This is assignment. So we are updating Q to be Q minus the set that only has V, because once we have chosen V here, then we remove V from Q, just so that we don't so it does not become an endless loop. Okay. Well, we still have 2 more minutes, so I can continue to talk about the rest. For each edge, okay, so what does that mean? Look at this notation here. What does that mean? This notation here. So we have chosen V from here, and now we're basically looking at all the incoming edges to V. So we're basically saying for each incoming edge of V, do the following. basically what we are doing is we are saying, okay, V, you look the most promising, okay? You're the closest to a bathroom, okay? But, so what other locations are immediately adjacent to location B? Because those locations may go through V to get to a bathroom, and that may be the shortest path to a bathroom. That's what it's doing. So from this perspective, because of the way we choose V here, it relates to something that we saw earlier. It relates to the term of a greedy algorithm. So Dijkstra's algorithm is known as quote unquote a greedy algorithm because of all the alternatives that we can choose. We're basically saying, of all the things that we can choose, let's pick the one that is already closest, known to be closest to a bathroom. And then we'll explore that one. We'll explore the other locations immediately around that one vertex. Hopefully, those things will go through this particular vertex to find their own shortest path to a bathroom. I'm not sure whether that makes sense or not, but that's what greedy means, in terms of algorithm design. And I think it's a misnomer. I think that it really should have been called optimistic. But that's just me, okay? I think it's just, greedy is not really a proper description of, the fact that we are choosing the vertex to expand using this particular method. So there we go. Okay, so next Monday, when we get back, I'm going to finish describing the rest of the algorithm, and then I'll be working on a particular example. For those of you who really want to kind of move ahead and kind of do this yourself, you can also try to make a graph yourself. You give me that graph so that I can use your graph as an example in class as well. So that might be a good exercise because now you can kind of think of tricky scenario like, what if I do it this way? Can I trick the Dijkstra's algorithm to find a non-optimal path initially? And then later on, it goes like, darn it, that was not the shortest path. Let me fix myself. So things you can think about. Have a nice weekend. I'll see you on Monday. Yep, you too. Yep.
So the first bullet point that you, so we